Welcome to my first physics video for Chiltern Cantelo School. Having completed our first look at light and lenses, we're now going to look at the physics of sound. As the Beach Boys, a 60s pop band, had it, sound is good vibrations. In fact, the biggest difference between sound and light is the type and frequency of those vibrations. Light is transmitted as a transverse wave, whereas sound is transmitted as a longitudinal wave, as we can see in this illustration at the bottom of the screen. Be ready to create a spider diagram or a mind map of what you know about sound at the start of lessons on Tuesday next week. In the lesson we'll do some experiments to learn more about sound. The key things to note are that sound needs a medium, unlike light, to travel through. By a medium I mean a substance, the simplest of which is probably air. The sound will also travel through metal, wood and bone. We can illustrate that with this vacuum pump. We'll take the air out and we'll notice that the sound goes away. The reason you think your voice sounds different when you play it back from a recording, as I would be doing here, is that normally you hear your voice not through the air but through the bones in your head, whereas we all hear your voice only through the air. And because sound travels at a different speed, it sounds very different to you. How do we create sounds? Simply, we make something vibrate. This vibration makes the air nearby compress and expand in time with those vibrations. This change in pressure then propagates or spreads through the air. The simplest item we can make vibrate is our own vocal cords in our throat. Try it. Say a word. That's it. You've made your vocal cords vibrate, and this has made a sound. You hear the sound, and so do those nearby. The sounds we make as words are a jumble of sounds, but some musical instruments make much simpler sounds. If you look carefully at a guitar when it's playing, you can see the strings vibrating, especially the bass strings, because they vibrate the slowest. Other instruments, like the flute, also make air vibrate, and that makes a much purer tone. The tuning fork probably makes the purest tone of all. We use that for tuning our guitars and our pianos. The metal just vibrates, and that creates the compression wave going through the air, as you can see here, illustrated on this diagram. Here's another illustration of that, showing how that wave propagates through the air. And if we measure the distance between the two nearest compression points, we call that the wavelength. And from that we can also work out the frequency, how often the tuning fork is vibrating. Here's a video of one touching water to see just how much the tines of the tuning fork actually vibrate. It's much greater than you expect because they're vibrating so fast. Here's a loudspeaker showing the creation of a tone, and here again is an illustration of that travelling through the air towards our ears. The sine wave below is an illustration of how that would look if we were to look at that using a microphone connected to an oscilloscope. We'll be doing that in class as well. We'll also play with a slinky. We can send a compression wave through the slinky. It's interesting and important to note that the actual metal doesn't move very far. Each piece just moves backwards and forwards in place. It doesn't move from the source to the destination. Only the energy and the sound travels from the source to the destination. So here again is that compression wave illustrated from the tuning fork. We can represent this simple illustration just by two parameters, the frequency and the amplitude. The frequency is a representation of the vibrations per second, how fast the tuning fork is actually vibrating. We measure that unit as the Hertz, or Hz, and that's because it's named after Heinrich Hertz, who was a pioneer in radio waves. He made sparks and then measured the waves, and they are also measured as a frequency, and so we now use his name as the unit of measure. Here we see an illustration of different sound waves of different frequencies. Human hearing covers roughly 20 Hz up to 20,000 Hz. So here we see at the bottom a bass note made by the bass guitar or a double bass in the region of 40 to 100 Hertz. As we go up the frequencies get faster, up to the mid-range, which can go up to 2000 Hertz, which is now pretty much beyond our piano, and all the way up to high frequencies, 10 up to 18 kilohertz or 18,000 Hertz. Some of you might still be able to hear up to 20,000 Hertz, but as we get older, our range of frequencies gets smaller and smaller. Here's another representation of two waves, one with low frequency, we see the symbols spaced out here along the bottom, and a higher frequency where they're happening more rapidly over time. We can also measure the size or the amplitude of our waves, and here we see three different waves at three different amplitudes. We might also call that the volume. So this top sound is the quietest, getting louder, and the bottom sound is the loudest because it has the highest amplitude, which we measure from the center line to the peak of the wave. And here we see that again illustrated here. The amplitude from the center line to the peak, and the wavelength we measure from one peak to the other. And wavelength and frequency are directly in a reciprocal relationship to each other. So the key things to remember from this video: sound needs a medium to travel through, such as air, but also through bone, metal, and any other solid or gas or liquid. Sound is a compression wave, that is to say it's a longitudinal wave, unlike light, which is a transverse wave. We measure its frequency, which we might also call pitch in music, and we can measure its wavelength, which is directly and inversely proportionally related, and we can also measure its amplitude. So if you can remember these key things for class on Tuesday, then we'll get off to a really good start. Thank you for watching.